So this chapter is on observations, but I also kept mixing data into it, as you will see in the rest of the podcasts. So I added this podcast after recording the others, so you will see some jump in the second podcast. But nonetheless, when we say observations, it's obviously showing the results from all the data we already have typically, and nowadays the definition of data is also a bit fudged, in the sense we have the so-called reanalysis products, where the existing data are blended with existing models and integrated in with various methods like data assimilation as a broad terminology, and that is kind of a dynamically interpolated data that fills the gaps using model construct, model framework, model integration. So people call that data as well. But if you go and Google climate observations, or you will get schematics like this. This is the Global Observing System. There is a program also called GEOS, GEOSS, Global Earth Observing System of Systems, and so on. So climate observations and Earth system observations can be technically different, where climate observation can be just focused on physical and biogeochemical aspects, and Earth system can include humans, human activities, and so on. But nonetheless, you see here there are aircrafts, there is satellites, there are ocean data buoy, there is ships, weather ship and satellite soundings, polar orbiting, geostationary and satellite images, ground stations that help you track satellites and convert satellite observations into data. Upper air stations, there are radiosondes, balloons, surface station, and so on, weather radars, automatic stations, etc., etc. And obviously the key aspect of observations these days is all heading towards climate change and global warming. So here is the number of stations that are observing CO2 across the globe. Mauna Loa is of course the oldest one, that started in the 1950s, which we will revisit in another podcast. Here we have monthly annual CO2 concentrations at Mauna Loa. So the smooth curve and the seasonal variations are shown. CO2, we will see later on, is a well mixed long residence time gas. So if you measure at one or two stations, you get a good sense, but a lot of stations are added to do other detailed work on sources and sinks and countries, contributions, and so on and so forth. Just to give you a sense, these are just the volunteer observing ships, which have been collecting data for many decades, in fact. So these are the position and number of observations per format, and last location and number of active platforms per type. So here the observations, you have various climatological, automated, climatological, manned, volunteer observing ships, automated and manned, and they carry typically thermosalinographs and etc. And we will see in the further podcasts another map of ocean observations, which include moored observations, tide gauges, and so on. So moored observations typically look like this. This is a map from Hui, which is anchored to the bottom. There is a surface buoy carrying a anemometer, air temperature, and relative humidity sensor. So winds, relative humidity, air temperature. Oftentimes they also have precipitation observations, sometimes also other flux parameters. There is a special wire or nylon termination So you have buoyant polypropylene, so 17-inch glass flotation balls in plastic hard hats, acoustic release, so the mooring can be disconnected using acoustic release, and you can have thermistor chains along the way. You can have salinity, you can have current meters, and so on and so forth. One of the more exciting platform that has evolved recently, since about 2000, 2004 or so, is called an Argo float. So it is deployed, let's say, from a ship. Nowadays they're also being dropped from an airplane or a helicopter. So it descends to a depth and is parked there, and every few days it comes up, beams the data to the satellite, and it collects data like temperature and salinity. And as I will mention again later in the other podcast, the reason for keeping it down here is that the currents are very weak, so it doesn't drift too far from where it is supposed to stay, and there is no light and biology that can grow on the instruments or on the buoy at that depth. Anything you put near the surface tends to have growth of biology, organisms, and then becomes what is called a fad fish aggregating device, and so on and so forth. So this avoids all that. Plus it also provides a nice continuous profile all the way close to the surface to about, let's say, 5 meters or so. So we will see a map of how those are distributed around the world's ocean. Typically, when you want to think about observing and collecting data for any particular purpose, you are either focused on forecasts, let's say at weather time scales, as we said. So they will be initialized forecasts for a few days or a week. Initialized predictions can be seasonal to interannual, or nowadays there are also attempts to make decadal climate predictions as well as decadal Earth system predictions. And of course we are also now engaged in projections under the IPCC Intergovernmental Panel on Climate Change, which obviously looks into future with scenarios and beyond emissions scenarios. So larger space scale, longer time scale affects smaller space scale and shorter time scale in this continuum of multi-scale interactions. You have natural modes like the Pacific Decadal Oscillation, Atlantic multi-decadal oscillation, meridional overturning circulation, which we are not introduced yet in this course, but it is something we will visit. Seasonal and interannual, so what happens at a seasonal time scales and year-to-year time scale. So we will already mentioned El Nino, and it's also called El Nino Southern Oscillation, which we will learn later. Tropical biennial oscillation, monsoons like the Indian monsoon, Asian monsoon, Australian monsoon. There are sub-seasonal processes like the Madden-Julian oscillation, synoptic scale weather systems, and then you have smaller space scales and shorter time scales affecting larger space scales and longer time scales going the other way. Okay, so the World Organization, like the World Meteorological Organization, along with the scientific communities, defines what are called essential climate variables, which are any physical, biological, chemical variables that affect Earth's climate. So you have the upper air atmospheric variables, you have surface atmospheric variables, atmospheric compositions, dust, chemicals, clouds, and so on. Cryosphere, which is the frozen part of the Earth's system. Anthroposphere, where human activities are tracked in terms of emissions, land use change, deforestation, etc., urbanization, agriculture, and so on. Surface ocean physics parameters, temperature, waves, currents, air-sea exchanges, etc. Ocean biogeochemistry, including carbon, nitrogen, chlorophyll, oxygen, whatever else. Ocean biology and ecosystems, so chlorophyll comes in there, could include marine ecosystems and so on. Subsurface ocean physics, obviously, and biosphere, vegetation, agriculture, various uses of fertilizers, deforestation, wildfires, and so on, and hydrosphere, which is all the water parts. So that's how data are collected and observations are made. So we will run through a number of observations at mostly climate change timescales in physical variables, cryosphere, biogeochemistry, and then look at some of the uncertainties we get in the data that we use to make these observations. So I wanted to add this at the beginning because I think I started the other podcast of this chapter focusing more on data rather than observations. So please go through them. I do explain all the observations, but we'll come back to those physics later on again. So no loss.